The relation A related to B if absolute value of A is less than or equals to B is defined on the set of real numbers. Find whether the relation is reflexive, symmetric, or transitive. Okay, let us begin. So here we have a relation R. So R is defined on the set of real numbers. That simply means that R is going to be a subset of the Cartesian product of the set of real numbers with itself. And we have a relation ARB. That means R is going to be a set of ordered pairs A comma B such that we have absolute value of A that's going to be less than or equals to B, where A and B belongs to the set of real numbers. That means A and B are real numbers. So this is our relation. And we have to check whether if the relation is reflexive, symmetric, or transitive. Now in order to show that, let's quickly go through the definition. So here R, let's say, is a relation on the set A. R is going to be reflexive if and only if the ordered pair A comma A belongs to the relation R for all A belonging to the set A. That means for all the values that we pick up from the set A, the ordered pair A comma A must be present in the relation. Then we can say that R is reflexive. R is going to be symmetric if the ordered pair A comma B belongs to R, implies that the ordered pair B comma A, where B comma A is obtained by interchanging the elements within the ordered pair of A comma B, must also belong to the relation R for all A and B belonging to the set A. That means any A and B value that we pick up from the set A, if A comma B belongs to R, then B comma A must also belong to the relation R. Then R is going to be referred to as a symmetric relation. Next, we need to check whether if R is going to be a transitive relation if the ordered pair A comma B belongs to R. We have another ordered pair B comma C belonging to R. This implies that the ordered pair A comma C belongs to R for all A, B, and C belonging to the set A. Now here, while choosing the two ordered pairs A comma B and B comma C, we only have to make sure that the second element of the first ordered pair A comma B, which is B in our case, that matches with the first element of the second ordered pair B comma C. Okay, so let's start with the problem. We'll first check for reflexivity. We'll check whether if the relation R is reflexive or not. Okay, so for this, let us consider an arbitrary element A. So let A be an arbitrary element such that if we consider A belonging to the set of real numbers R, this must then the ordered pair A comma A belonging to the relation R must imply that absolute value of A is going to be less than or equals to A. So here we are using the definition. So instead of absolute value of A less than or equals to B, we're replacing this B with A. Now, is this a true statement? Is the absolute value of A less than or equals to A? No, this is not a true statement. This is not necessarily true. Why? Let's try to understand this. The moment we write absolute value of A less than or equals to A, now let's say if we consider positive real numbers. Instance, let's say A is positive 2. In that case, we can say that the absolute value of 2 is less than or equals to 2. So this is a true statement. That's fine. That makes complete sense. However, if we take A to be some negative number, so let's say A is negative 2, then we are saying that absolute value of negative 2 is less than or equals to negative 2. But we know that the absolute value always gives us a positive value. It gives us the magnitude. So here this is going to be 2. In this case, we're getting the 2 is less than or equals to negative 2, and we know that's an incorrect statement. So this simply means that the inequality absolute value of A less than or equals to A, this is not necessarily always true. It is only true for specific cases. That means only when A is positive, not true when A is negative. In other words, we can say that our given relation R is not reflexive. This is not a reflexive relation. Okay, fine. Let's now check whether if it is symmetric or not. So we're going to use the definition for symmetry. For this, we're going to consider two elements A and B. Let's say these two elements belong to the set of real numbers such that if we consider the ordered pair A comma B, this ordered pair must belong to the relation R, then it must imply that according to the definition, absolute value of A is going to be less than or equals to B. That's what it means. That is the definition. The ordered pair A comma B belonging to R. But this does not necessarily mean that absolute value of b is less than or equals to a. This is not necessarily true. So let's check this with the help of an example. So we are saying that absolute value of a is less than or equals to b. Fine. So here we have a and b. These are two numbers. If we consider positive values, so if we consider a to be equals to 2 and b to be equals to 3, this makes perfect sense. Absolute value of 2 is going to be indeed less than or equals to 3. Fine. 2 is less than 3. However, if we choose a to be equals to -2 and b to be equals to -3, then what we are getting? So here we're getting that absolute value of -2, this is less than or equals to -3, but we know absolute value, this is a positive value. So this is not going to be a true case. So hence we can say that b comma a does not belong to the relation R. Since b comma a cannot belong to the relation R, so we can say, so relation R is not symmetric as well. So this is not going to be a symmetric relation. Fine. Now we finally come to transitive relation. So here we're going to check, we're going to consider two ordered pairs a comma b and b comma. So let us consider the elements a, b and c belonging to the set of real numbers, such that if we consider the ordered pair a comma b belonging to R, and we also consider another ordered pair b comma c belonging to the relation R, our goal will be to verify that a comma c also belongs to the relation R. In other words, we have to show that absolute value of a is less than or equals to c. Only then we can say that the relation R is transitive in nature, or else it is not going to be transitive. Okay, fine. So since a comma b belongs to the relation R, we can say here that absolute value of a, that's going to be less than or equals to b. And we have b comma c, the ordered pair b comma c belonging to R. This means that the absolute value of b must be less than or equals to c. Now we're going to combine these two inequalities. We're going to multiply the corresponding sides. So the left hand side gets multiplied to give us modulus of a times absolute value of b is going to be less than or equals to b times c. Now absolute value of a times absolute value of b, this is simply absolute value of ab less than or equals to bc. Fine. Now what we can do, we can expand this inequality to rewrite it as negative a, that AB is going to lie between negative BC and positive BC. Now what we can do, we can divide throughout with B, assuming B is positive. So assuming B is positive, so this means that we have negative C less than or equals to A less than or equals to C. Or in other words, what we can do, we can combine this inequality and rewrite it as absolute value of A is going to be less than or equals to C. So this is exactly what we have shown. So this means that A comma C must belong to the relation R. So we can say that R is going to be transitive. So here for this particular relation R, so for the particular relation R, which is defined as absolute value of A less than or equals to B, it is going to be a transitive relation, but it is not going to be reflexive, nor it's going to be symmetric.